All of our previous description of the theory behind inertial navigation systems assumes that the system is up and running. The platform is levelled and north-orientated. It is therefore necessary to initialize the platform before flight in order to get it level and orientated. This process is called alignment. Details of the various stages of alignment vary from manufacturer to manufacturer, with some using stages known as course levelling, course alignment, fine levelling, and fine alignment. However, all systems share the same three broad stages. These are caging, levelling, and gyrocompassing. The gyros used in INS spin at about 25,000 revolutions per minute, and some designs are quite heavy. Usually, we need a powerful motor to spin them. However, at startup they are static and so have no rigidity. The gimbals and gyros could be in any position. It simply depends on where they stopped when the gyro ran down after its last use. If we suddenly start these powerful motors without parking the gyro in a safe configuration, we could damage the gyro or gimbals. The inner gimbal is therefore driven to a position at 90 degrees to the outer gimbal, and the outer gimbal is driven at 90 degrees to the frame. This is called caging. We can now run the motor up. Additionally, to give good stability and accuracy, the gyro needs to be run at a constant operating temperature within a narrow band of limits. Once it is up and running, we need a ventilation system to get rid of the waste heat. However, in order to get the system at temperature quickly, we apply heater voltages initially. This whole process takes about 3 minutes and is fully automatically controlled by the computer. Once it is complete, alignment proceeds to the next stage, which is levelling. It is absolutely essential that the gyros are as level as possible before we start. You remember that we said that accelerometers can be compared to spirit levels. You can either use them to measure horizontal accelerations or to establish the horizontal, but not both at the same time. However, during the alignment process, we don't need to measure horizontal accelerations. The aircraft is on chocks. It isn't going anywhere. The accelerometer output should be 0 for a stationary aircraft, but if the platform is tilted, it senses a component of gravity along its sensitive axis. During levelling, these outputs, instead of being integrated into velocities, are passed directly back to the levelling motor, which tilts the gyro and platform back until 0 acceleration is sensed. At this point, the platform is levelled to the local gravity vertical. Levelling also takes about 3 minutes. The system now automatically proceeds to the next stage, which is gyrocompassing. Gyrocompassing is the process of rotating the platform so that it takes up an orientation of true north. Gyrocompassing senses the heading with reference to the Earth's spin axis, which is true east. Note that Earth magnetism is not used. It depends on the principle that an ideal gyro, being space-referenced, can detect Earth rate. In the high-quality gyros used in INS, the real wander is so low that they can be considered as ideal gyros. This picture shows that if the gyro axis is pointing east at the equator, the gyro will be sensitive to Earth rate. Whilst this one shows that if the gyro axis is pointing north, there is no Earth rate at the equator. This horizontal component is, as we showed earlier, 15 times the cosine of latitude in degrees per hour. At the equator, we get the full 15 degrees per hour when pointing east, and 15 times the sine of the latitude in degrees per hour when pointing north. This is 0. At any other latitude, we get intermediate amounts, depending on the latitude. As gyrocompassing starts, the platform has been levelled like this. But as the Earth rotates, the platform initially stays rigid in space. The aircraft, which is still on chocks, stays with the Earth. This will cause the accelerometers to detect gravity. The platform is therefore rotated by servos until the accelerometers stop detecting gravity. This means that the gyro axis must be pointing north. This is taken as the reference heading for the INS. Gyrocompassing takes about 11 minutes at medium latitudes. So, with approximately 3 minutes for caging, 3 minutes for levelling and 11 minutes for gyrocompassing, the entire alignment process normally takes about 17 minutes, though it does vary with latitude. The INS needs to know starting latitude in order to calculate the correct Earth rate, using 15 times the sine and cosine of latitude degrees per hour. If the latitude inserted at startup is wrong, the alignment will be incorrectly computed. In fact, if the latitude error is considerable, the INS may not align at all. Examiners sometimes set questions using a figure of 10 degrees of error as the limit. Note, however, that longitude is not used in the alignment calculations. If an incorrect longitude is inserted at startup, there will be a present position error, but it will not affect the accuracy of the alignment. Therefore, we can say that INS alignment is sensitive to incorrect latitude, but insensitive to incorrect longitude. We now come on to why it was necessary for you to understand that the vertical component of Earth rate depends on the cosine of latitude. It is the cosine of latitude that determines the amount of Earth rate which we can use for gyrocompassing. Cosine is a function that gets smaller as latitude increases. This means that the accelerometers are trying to detect smaller and smaller amounts of Earth rate as latitude increases. Thus, an alignment at high latitudes takes longer than one at low latitudes and is slightly less accurate. However, at very high latitudes, the amount of Earth rate is so small that it is swamped by the error tolerance of the accelerometers, and alignment is not possible at all. This occurs at around 70 to 75 degrees north or south, depending on the vintage of the INS. If ground alignment can be achieved at a lower latitude, the aircraft can be subsequently operated at high latitudes, but it cannot be initially aligned at high latitudes. We said earlier that if you move accelerometers sideways, you can't use them for measuring the vertical. Therefore, the aircraft cannot be moved at all during the alignment process. The slightest movement off chocks will destroy the alignment and you will have to start again. With many aircraft, it is not possible to align with engines running. Even gusty wind conditions can prevent alignment. Alignment is completed when the Ready Nav light comes on. The MSU selector can then be moved from Align to Nav, and the aircraft can be subsequently moved without damaging the alignment. Let's summarize this lesson. Alignment takes place in 3 stages: caging, leveling, and gyrocompassing. Caging the gimbals protects the gyros whilst they are being spun up. The gyros are also warmed up. It takes about 3 minutes. The system then automatically proceeds to the levelling phase. The accelerometers are used as gravity detectors, and the platform is erected to the local horizontal. This also takes about 3 minutes. Gyrocompassing is the process of rotating the platform so that it takes up an orientation of true north. Gyrocompassing senses the heading with reference to the Earth's spin axis, which is true east. It takes about 11 minutes at medium latitudes. So, with approximately 3 minutes for caging, 3 minutes for levelling and 11 minutes for gyrocompassing, the entire alignment process normally takes about 17 minutes, though it does vary with latitude. It is essential that the correct initial latitude is entered. However, an incorrect initial longitude does not degrade alignment. Alignment is limited to latitudes of less than 70 degrees or so. If this is achieved, the aircraft can be subsequently operated at high latitudes, but it cannot be initially aligned at high latitudes. The aircraft cannot be moved at all during the alignment process. Even the vibration from a running engine or gusty wind may prevent alignment. This concludes the initial lessons on IN theory. We shall return to it later when we consider IN errors, but the next lesson looks at practical operation of the equipment.